Computational quantum logic. Yeah, the title was there when I sent it, I swear. But I don't know what happened. Anyway, so it's towards computational quantum logic. So the motivation behind this work is try to define a quantum proof language for some intuitionistic logic. So we have to define what is the logic that we want, but we want that the proof language is a quantum programming language. That is the main point. So the strategy has been first to modify a proof language from a known logic, trying to accommodate quantum programs and see what we have to add. Then we started from the opposite direction, from the opposite end, to modify a well-known logic, trying to accommodate the quantum programs, trying to meet in the middle. Okay. So let's start from the first end, modifying a quantum language to accommodate quantum programs. So what is quantum computing? Very easily, just for this slide to be understandable, we can think of quantum computing as unitary maps and measurements. Okay, unitary maps over vectors, those are the qubits. So we need to take the lambda calculus and being able to express these two things. So there has been a work by Pablo Rigui and Gildo Weck 15 years ago, where they defined a language where you can superpose terms. So the idea of the language is that if U and B are two terms, then this linear combination is also a term. And they define this strategy that they call by base, because these two can be seen as the base of a vector space, where a lambda term will distribute over the linear combination. Okay, that is called by base. And in this work, what we did is 12 types to it. So first, we say, okay, if this is an arrow from A to B, and this is a superposition of type A, then we mark it with an S, we mark it with something, and what we obtain is a superposition of B. Then, well, there should be a parenthesis here. A matrix can be represented in this way. Just take a bit, and then you say, if it is true, you reply with this. If it is false, you reply with this. And then this is, any vector can be represented as A true plus B false. And when you apply this matrix to this, alpha beta, what you will do is this strategy will go inside, and then it will do exactly the matrix multiplication. Okay? So this is the linearity part. The problem is that, as I said, here you have unitary maps that are linear, and you have the measurement. The measurement is an operation that is not linear. So if you do this, if this represents my qubit, I don't want the measurement to go inside and see what is true and what is false. It has to take the whole superposition to measure it. So what we did in this work is just to guide the reduction by the type, saying, okay, if it is a superposition, what you will get, then you just do call by name. But then here we use a linear logic style, in the sense that we will ensure that this variable is not used more than once, okay? Because in quantum computing, you cannot duplicate qubits. That is a no-cloning principle. So you have this linearity here, and the non-linear part, you treat it kind of in a linear logic style, okay? So, and this linearity is kind of tricky, because what we are saying is not that this function is linear, is that we force the linearity in this function. So you don't need to ask this function to be linear. You just, by definition, it is linear. It distributes linearly. Okay. And then the unitarity part, we did it in another work where we use a reusability model, but I will not speak about it because I only have 15 minutes. But the idea was to take a model where in the model everything has norm 1, and then this induces the type restriction that we need just to restrict this not only to be linear, but to be unitary. But the main point from this slide that I want you to keep is that this idea of forced linearity for the non-linear function, so this is not a linear function, but you force it, and the superpositions which are the non-duplicable terms, which are treated linearly, okay, in the sense of linear logic. These two things. So then we saw that this is kind of, okay, I miss a P here. That is my fault. This is kind of a sort of opposite to linear logic, in the sense that in linear logic, you will mark what is duplicable. Here we are marking what is not duplicable. And in fact, we, in a series of work, we did a model for this, where we saw that we can use an assumption between a Cartesian closed category and an additive symmetric monoidal closed category, for example, set and vector spaces. And to interpret our calculus here in the Cartesian closed category, but to use the assumption to interpret the S, this S mark is interpreted as the monad. Okay, so you pass to the vector space, you do whatever you need, and then you use the forgettable functor or whatever. While in linear logic, it is exactly the opposite. So you interpret the calculus here, and then you use this assumption in the other direction to interpret the bank. Okay, so this is kind of a dual or opposite to what you do in linear logic, and we arrive to this by considering these superpositions. So the second part is to modify a logic to accommodate quantum problems. Okay, so to try to start from the other end. So here the first question we had was, what happened with the non-determinism that you get with the measurement? The measurement is a probabilistic thing, but even the non-determinism, what is it in logic? So we thought about what could represent the superposition. So we say, okay, let's consider the superposition is like a conjunction. You have both things, but when you measure it, you get one of them, not non-deterministically or probabilistically. So it is kind of, the introduction is a conjunction, but the elimination is a disjunction, where you don't know if you have A or B. But here you could have both, in fact. So what we did is to add this new connective that we call it sup for superposition, which has the introduction of the conjunction, the elimination from the disjunction. And then here, the cut elimination creates a non-determinist because if you have both A and B, you can use either this part of this part to conclude, okay? So you have the non-determinist there. But of course, that the superposition is not only non-deterministic. In the superposition, you also have the unitary maps, for example. So this is a way to say, if you have the superposition, we will interpret as this introduction, but you can eliminate it in this way. But we could also want to eliminate it in a way that we keep everything, for example, with to interpret a matrix. And then we added this rule that says if you have a proof of A and you have a proof of A, then you have a proof of A. So it's really hard to understand. But with this, we say, okay, we can just say that if we don't want the non-determinist, we can reduce using both, and then you join both with this rule. And this rule, in the proof terms, become a rule for that we call it addition. But the idea is you have a proof of A, you have another proof of A, then the addition is the proof, is the proof of A you want. And then we started putting things and say, okay, now that we have the non-determinist and the deterministic part, we need the scalars from that you have in the vectors in quantum computing. So we add the scalar with this rule that is even harder than this one. It says if you have a proof of A, then you have a proof of A. But it adds a scalar, and that is the interesting part. And then we also have the scalars for the unit. Then with this construction, we show that, of course, there is a one-to-one correspondence between the sup of several tops with the complex to the end, because we are just putting the scalar here, so we are just putting scalars. But the interesting part is that the sum that we have here becomes exactly the sum of in the vector space, and the scalar becomes the scalar product in the vector space. So that is the interesting part, if you want. So with this, we were able to to encode matrices and vectors and then quantum computing, and also a measurement where we have to do some modifications so the reduction is probabilistic instead of non-deterministic, but it is done in that paper. Then we move to linear logic because we say, okay, we still need the non-duplication part. So in linear logic, this subconnective becomes an additive connective. This is intuitionistic linear logic, so I put in gray what is not there because those connectives are not intuitionistic. And then here what we were able to prove is that every function, every program that we can write is linear in the sense of, well, algebraically linear. So this is a term in the calculus that, of course, you have a linear type system, but then you can express the linearity even in the terms, in the syntaxes of the term. That was the point. So the last piece of work that I will show, is, well, then we realized that we could get rid of this new connective just to stay in something more standard. If you consider this is the disjunction, well, it's the additive disjunction in linear logic, the plus, the introduction and the elimination. So what we are saying is just that we are adding a third introduction rule that do something like this. You take both and then you introduce both. This in-LR, because it's just the introduction of the pair, but the thing is that since we are using the same symbol, we can match it with this, and then we have again the non-determinist, and we can do the same trick as adding the sum if we can recover the determinist and everything without needing this new connective. So the idea is that it's only with this new introduction that makes completely sense in linear logic because well, in any model this is normally a byproduct. So this is just the pair because it is a byproduct. So it is a conjunction and a disjunction. And then just by curiosity we say, okay, but this also works if we are not in linear logic where we don't have byproducts. And then we try to study what happened in propositional logic, because in linear logic, okay, byproducts in an additive category do the trick, but in propositional logic, what do you need to do? And we came up with this funny operation that is just, you take one, the other, or just both, and it surprisingly works. So this is just an abstract. And that's all. So summarizing, what we have is this lambda S, which is interpreted in this side of the assumption, and this linear sub, well, with a bang that is in this work, calculus that is interpreted in this other side, but exactly with the same categorical construction.